Okay, so first example of the day, approximations with Taylor polynomials. It says approximate the given quantities using a polynomial with n equals 3. N equals 3. So what does n equals 3 mean? Number of terms or the power of the polynomial?
Two.
So if we look at our Taylor polynomials, so the nth order Taylor polynomial is referring to the power and number of terms. Power. Not number of terms. There's always going to be one extra term unless it happens to be some zeros. Yes. If f of a is 0, then there would be one. If f of a is 0, then it would match. Or if it's not 0, it's going to be one extra term. Okay, so n is equal to 3, which in general will mean 4 terms. Okay, so when we go to do this, we have to be super neat. And what's the function that we are going to use to build the Taylor polynomial? What function? Tangent of x. So that's where we're going to start. So we're going to take the function and its derivatives, and this is going to get a little messy, right? Because the derivative of tangent is secant squared. And then we have to take that derivative. We'll have to use the chain rule in conjunction with the power rule. So the derivative here is going to be 2 secant squared of x tangent of x, I believe. Do you agree? Do you agree? Everyone agree with that derivative? Power comes down, subtract 1 from the exponent, so you get secant, but then you take the derivative of secant. The derivative of secant is secant tangent.
Still secant squared.
Yep, should be secant squared. Yeah, it should be. Because the 2 comes down in front, you have 2 secant to the 1, but then the derivative of secant is secant tangent.
Yeah, the double derivative, it's 2 secant squared. You didn't erase the power off.
You need 2.
But, okay, I'm just not.
What's the derivative of secant?
Secant tangent.
So,
right.
you see it? Okay, we're going. We're warming up, folks.
Feels like a Monday.
Feels like a Monday, but it's not.
I almost went, it is a Monday. It's like a Monday for us, for sure. Okay, so we're going to n equals 3, so we have one more derivative. So now we have to use the product rule. So first derivative second. What's the derivative of second? So first function, 2 secant squared, derivative of tangent is secant squared, so we end up with 2 secant to the 4th. So that's first derivative second, plus the derivative of first times the second. Well, the derivative of first, we just did it. Essentially, it's right there, right? So what should we have here?
Four secant squared x tangent squared x.
Yes.
Waking up, guys.
I think you said it right. So the derivative of this, again, the 2 comes down, makes that a 4. It's secant to the 1, but the derivative of secant is secant times tangent, and then we're going to get a square on there. All right, so derivatives, calc 0. And then we have to evaluate these at our center. Where's our center? I think I heard it. So we can choose the center that we want. So the idea with an approximation is that we're going to choose the center to be as close as possible to the x value. Negative 0.1 is the x value. So we want a center that's really close to that we can evaluate the function at without using any technology or anything like that. So the number closest to negative 0.1 for which tangent is easily evaluable? 0. What's tangent of 1/10? You don't know tangent of 1/10.
I thought you were saying just like 0.1.
Well, we want to pick a center that's really close to that for which we know tangent's value at.
It's literally negative 0.1. That's crazy. Look at this. This is weird.
I know, it's weird. So y of 0 is 0. Y prime of 0 is what? 1. Cosine of 0 is 1. Y double prime of 0? 0. Y triple prime of 0? 2. So now we build our polynomial. So we're going to 3, so we're going to call this p sub 3 of x. So it's a third order polynomial. It'll have 4 terms unless one of the terms has a 0. Oh, this one has a 0. So we start with the constant. We'll put it in just to make sure the pattern is obvious. So it's 0, constant, plus 1 times x minus 0 to the first power. So x minus the center. Then we go to the next constant. Ooh, another 0. This would be 0 times x squared divided by 2 factorial if we completed the pattern. Obviously, we'll wipe that term out in a moment. Plus the next constant, 2 divided by 3 factorial times x raised to the third power. So that'll be p sub 3, which let's just simplify that a little bit. And we can cancel out this 2 in this case since we're doing a little bit of simplification. In general, you don't have to simplify, but there is our p sub 3. So that is the third order Taylor polynomial. It's the best cubic approximation to the curve at 0. Best cubic approximation. It's the glorified tangent line. Then we want to approximate. So we're going to do p sub 3 of negative 0.1. Picking 0 because it's closest to negative 1/10 for which we know the value of tangent. Okay, so all we're doing is plugging in negative 1/10 for each of these x values. And that is our approximation, whatever this turns out to be. So it's going to be negative 10 times 10 is 100, 1,000 times 3, so 1 over 3,000. Common denominator of 3,000, so we'll multiply this one by 300 over 300. So we're going to get negative 301 over 3,000. So that's our approximation. Any issues with that? I'm just going to pull up non-logged in Desmos just as my calculator. All right, so negative 301 divided by 3,000. Now let's look at tangent of negative 1/10. So there is the more accurate value. Pretty accurate, pretty fast. So our approximation here, using a third order Taylor polynomial, is good all the way out to, you can see it, to whatever that number of decimal places is. Right, go down. So it's good out to, right in there. So out to 5 decimal places it's matching. And we only went to p sub 3. All right, any piece of that you have questions on? Okay, what did it say? So approximate, blah, blah, blah. Compute the absolute error in the approximation, assuming the exact value is given by a calculator. So the remainder is, let's first just plug it in here. So the remainder is the actual value, so that's this one, right? Minus, so the actual is the difference between these two. So we're just going to subtract the two. So if we take the actual and we subtract off our approximation, we just want to make sure, I'm going to subtract it in the other order actually, because the error should be positive. Right? Error is always going to be given to us as a positive number. So I'm just going to make this a positive, make that one a negative. Did I do that right? Positive number, 0.2. That's not right though. That does not seem right.
Divided by?
I think I subtracted wrong. Because when you subtract a negative, don't you end up with a positive? All right.
Shouldn't error be what you calculate versus actual, or divided by?
Not divided by.
Times 100 or something like that?
So
It's like percent error, right?
Yeah, just like percent closeness.
It's like actual minus what you got over actual.
I want to subtract it in the other order, so I'm going to make that one negative. What is happening here?
You have to do.
There we go. Yeah, there we go. All right. Yeah, okay, so we did this one minus the other one. Okay, so the error is always positive. So like when we say you're within, say, 1/10 of something, that means you could be above it or below it, but when we talk about error, we always talk about it as positive. So same idea with the remainder. The remainder, if we use the term remainder can be positive or negative, but if we change it to error, it's just the absolute value of the remainder. So error is always an absolute value. Remainder could be negative, though. So that's how close we are with this remainder. So we're within, 1 over 10,000 or whatever that is. I can't even read it. Too many zeros. So compute the absolute error. So when they say absolute error, that is overemphasizing that we put absolute value bars. The error is just the remainder minus the actual value. Take the absolute value. Or it's the actual value minus the remainder. Doesn't matter which way you subtract it, as long as you then take the absolute value. If you get a negative, make it positive. All right, so let's go ahead and try another one of these. So we have the log function here. So same idea. We're going to use the function, natural log of x. That's our function. So y equals ln x. And then what is the a value that we're going to choose, or the center?
0.
No. Natural log of 0 is not defined.
1.
1. That's the closest number to 1.05 that we can evaluate the log of.
I'm not sure it is English.
I'm actually it is Monday actually.
Harrison, do you have a question?
Well, no, because I was thinking, I thought you were saying to evaluate it what natural log of 1 would be, which isn't that 0?
Yeah.
Which is 0, not what natural log what the x would be. I thought you were trying to say y.
Gotcha. Yeah, so we want to pick an x value that's as close as possible to this. We want to pick a center value that's as close as possible to this x value for which we can evaluate the function.
That's a whole number.
It doesn't have to be a whole number. Like up here, if this was closer to pi over 4,
Okay.
right, we would want to pick pi over 4. So whatever pi over 4 is, like 3/4. If this was tangent to 1, then we want to pick the closest x value that we can evaluate tangent at without a calculator.
Okay.
So here we want to pick the closest, in this case it will be an integer, but if this was, say, natural log of 2.5, we would pick e, because e would be the closest x value, the closest center to 1.05, to 2,
Yeah.
point, whatever I said, 2.5.
Yeah. And if it was 1.5, would we do 3 halves?
if this was 1.5, we would have to see what's closer, 1 or e.
1 or e, okay.
Right, because the numbers for which we can evaluate natural log without any work are 1 and then multiples of e.
Okay.
So we pick whatever one's closest.
Okay.
So here, the number that's closest is 1. So we're going to choose the center to be 1. And then we evaluate each of these. So what is y of 1 then? What's natural log of 1? 0. And then y prime of 1? Y double prime of 1? Y triple prime of 1? Huh? What?
Negative 1.
2.
2.
What?
That's 2.
2 over 1.
So we're plugging a 1 in here. 1 to the negative 3 is 1 times 2.
6.
Killing me, Smalls.
Fine,
No way. This is a challenge.
Tomorrow's gonna be sick.
Challenge. Challenge accepted.
I heard it was like 2 to 4 inches.
Yep, 2 to 4. So constant first is 0.
I should hear. I have to drive my ankles.
And then it's going to be 1 times x minus the center. What did we choose for our center? So x minus 1 raised to the 1 power divided by 1 factorial if you wanted. Next constant, minus 1 times x minus 1 to the 2 divided by 2 factorial. And then plus 2 times x minus 1 to the 3 divided by 3 factorial. So there is P sub 3.
Fonts.
P sub 3, third order Taylor polynomial, best cubic approximation imaginable.
Factorial on this one back here, isn't that 6?
Yep, and then 2 divided by 6 is the third. Tweaking! You're tweaking? Not yet?
Not
Oh.
yet.
Someone in the back row is tweaking.
Oh no, I just have a question. So
Carter, I love my
like
teachers
this.
just sitting on the roof.
What about that?
Carter, we're gonna suck this out of you until the day it dies.
You keep it. They're going to be finite. They're not going to be like. So yeah, you should
But like on the test, would it be like ones that you could easily?
put into fractions. Yeah, yeah, they will be. You can fraction them.
There should be explanation.
All right, what we have now is the best cubic approximation. If we put the dot, dot, dot thing, we would have the series instead of the polynomial, and then it would match exactly.
And you'd dog points if we wrote the dot, dot, dot there.
Yeah, because we don't want the series. We want the polynomial. Polynomials don't have dot, dot, dot. Okay, now
Even that guy's mad.
what's happening out there? What is happening?
Dude, I almost
The car one?
macked the first one.
So what is the x value that we're going to plug in here to get our approximation?
1.05.
1.05. So 1.05. So here's our approximation. 1.05 minus 1 is 0.05. Let's write it as a fraction. It's a nickel. So that's a 20th. 20th of a dollar. So that's coming from here. You know about money, right?
No.
So then here, again, 1.05 minus 1 is 0.05. 0.05 is a 20th. And if we square a 20th, we get 1 over 400. But then if we multiply 400 by 2, we get 1 over 800.
Say that all again.
1.05 minus 1 is 0.05. 0.05 is a 20th. Right? 0.05 is a 20th, a nickel. A 20th. A 20th squared is a 400th.
Yeah, okay.
And then a 400th times a half is an 800th.
I do this every class when you're not here.
And then we get over here. This is 2 over 6, so this is 1/3. Right, that part's going to be 1/3. Same idea here. We have a 20th cubed. So that's going to be 1 over 20 cubed. 20 times 20 is 400. Times 20 is 8,000. Times 3. let's write it out this way just in case you're not 100% sure following. So now we just have to combine these fractions. We're going to agree here. This is got 3, so 20 times 20 times 20. We're going to have 3 zeros, so 8,000 times 3 is 24,000. Okay, now we just have to combine those together. Common denominator is 24,000. This one's going to be multiplied top and bottom by 30. So we're going to have negative 30 plus 1. This one top and bottom by 1200. So whatever that simplifies to. 1171? No. Yeah, maybe. So there's our approximation. Let's see how close it is. Let's see how close it is. How close are you? I guess. All right, let's see. So 117. And what was the function natural log of 1.05?
1.01, right? 1.05.
So if we, which one is bigger, the top one or the second one? Top one's bigger, so let's do that one. Let's do this one minus this one. So that is our error, our absolute error. Question, all right.
Wouldn't the absolute error be positive?
Yep, that's positive.
Why would that the negative sign?
So there's no, that's an equals.
Absolute error.
Oh. Really tiny.
I know, that's an equals. Here, I'll prove it to you. Equals.
Can I see?
What do you mean?
Equal. You can
Oh,
see
there
it.
it is. I couldn't.
You couldn't?
Can you put like a huge red circle on it?
On the equals?
Yeah.
No, I'm not gonna put a huge.
Just write it.
Put in your notes.
Just write it in the laser pointer.
A huge red circle. This is equals right there. We'll highlight it.
I don't know if that helps.
If we do all the equals are going to be highlighted today
Okay.
from here on out. All right, so there's the error. Error is super tiny. All right, let's go to our last slide in 11.1 because we want to get to 11.2. 11.2 is so hard, we want to spend enough time on it.
Is 11-2 gonna take the rest of class again?
Yes.
Yeah.
Are we going to finish it? Or-
We'll finish it. We'll finish it.
Okay.
Okay, so remainder. All right, so let's think about this and make sure that we're clear that this parallels what we did with our infinite series of numbers. We said that the sum was equal to S sub n plus R sub n. It's the same idea, except now we're dealing with a function. So here we're thinking of our function as being P sub n plus the remainder, and then the way they've written it, they've just isolated R sub n by subtracting P sub n over to the other side.
Where R sub n of x is a function?
R sub n is a function.
That's weird.
No, it's not. Depends on x. Right? If you think about your function f, when you plug in a particular x value, you plug that x value into P sub n, right? So P sub n is a function of x. So the remainder should also be a function of x. Right? The remainder is going to change depending on what x value you plug in. Because the function includes the whole infinite power series. P sub n and R sub n are just parts of it. So you still have to plug in the same x value. So R sub n is a function. Okay, so here is the part that's interesting, that we're not going to spend a lot of time on. This will be spent, you'll spend time on this in other classes. But remember in the alternating series how we went to the first unused term, and the first unused term gave us an estimate of the error, of the remainder. Everyone remember that? Right, you add up the first 10 terms, you go to the 11th term, and you take its absolute value, that tells you how close you are to the full actual sum. So the first unused term. And notice here we're going to do the same thing. If we look at our infinite series has terms that are of the form the nth derivative at the center divided by n factorial times x to the n, if it's centered at 0. If it's not centered at 0, this one's not centered at 0, there's an a, so that should be x minus a to the n. Right, that's what your general term looks like for your Taylor polynomial, or for your Taylor series. So notice, the next term will be the n plus first derivative over n plus 1 factorial, x minus a to the n plus 1. There's one difference between r sub n and the next term. What is the one difference?
Is this C?
Yes. Right? Normally we plug in a. Normally we plug in whatever the center is. So today we had a center that was 0, we plugged in 0. We had a center that was 1, we plugged in 1. Right? Whatever the center is, you plug it in to get the next term. What this is saying that's different is that we're plugging in the c value, and the c value is somewhere between the x value and the center. So the x value, we picked x values already. One was negative 1/10, and one was whatever it was before that. Right? So c is somewhere in between there. And notice that this is an equal here. The remainder equals the next term evaluated at some weird c value that we cannot find. This is a purely academic statement here. We cannot find the c. But we can approximate it. But we cannot find the c exactly.
Why not?
So this looks like, so with the alternating series, we said that that next term was an approximation of the remainder. Now we're saying the next term is the remainder if you plug in the right c value. But to get that c value, if you were to be able to find it, it's very, 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 very hard. 99% of the time you can't find it because you don't know what the remainder is. Right? So it's a theoretical result that can be proved, but you don't know what the remainder is, so you don't even know how to get closer and closer to c, because you don't know what the remainder is. So it's a theoretical result that we're not going to use in this class. But what you can do is get an estimate on the maximum value of this function here. And that's what this next statement says. It says, okay, well, there's this weird c, we can't find it. So the next best thing, because this function is defined on an interval between x and a, so you've got a closed interval, x to a, well, you graph that function and you figure out its maximum value. So if you can figure out a bound for the entire function, which most of the time occurs at one of the two endpoints, then you can get a really good gauge on the remainder.
Can we only not find C because the remainder is
It's not that it's an infinite series. The remainder itself is an infinite series. So it's the tail of the power series is the remainder, and you'd have to plug in that x value of whatever it is to all those terms. Here they're saying you can take that whole infinite series, collapse it into one term, evaluated at the correct c value. And it's just that to find that is virtually impossible. It's not like an equation you can just solve and get c. You would have to do a bunch of work to try to get it. But what you can do is graph this function. the n plus first derivative of f at x is a function. You can graph that and you can see where's its high point, where's its low point, and you can find the capital M. So this is the generalization of that alternating series remainder. In this class, the alternating series, that's where we are going to primarily focus on for remainders. This is more conceptual for us. Other classes will get into the weeds on this. In here, we're just going to say, oh, notice, it's kind of like the alternating series remainder, where you just look at the first unused term. So that's the only thing we want you to get out of it at this moment. All right, so that is the idea with remainders. Let's take a look at, anytime you have a new object, it's natural to say, well, how do you combine them? Right? You're given real numbers. How do you add them? How do you subtract them? You're given functions. How do you add them? How do you subtract them? You're given a new object now called a power series. The question becomes, how do you combine it with other power series? The scariest thing imaginable is to imagine multiplying two power series. Right? Adding them, you can imagine lining up the powers of x and adding them and subtracting them, nice and strategically. Multiplying them, nightmare.
Infinite foil?
Because you have an infinite FOIL. Yeah. Okay, so here we're going to talk about the most important power series in moving into the concept of power series. So back in the last chapter, we started with this infinite sum, and we said, oh, this is going to be called a geometric sum, a geometric series. What does it add up to? And this was sort of the result that we found, right? We found that. So we started with the infinite series. We found that result. We are going to turn this coin over. Now, we are going to replace the r with an x because we're imagining functions and not just a single constant. We're imagining x as being any constant that has a magnitude less than 1. And we're going to write, this is a function, right? You could graph f of x equals 1 over 1 minus x. You can graph that function. That's a hyperbola that's shifted and reflected. You can graph it. And we are going to write it as this infinite polynomial. So instead of starting with an infinite series and trying to collapse it into a sum, we're starting with what we called the sum of the series in the last chapter. We're saying, hey, wait, this is a function. And we can write it as an infinite polynomial. So this is the power series for that function. So for the geometric, it's the geometric series.
And it has the radius of convergence from -1 to 1?
Yep. So the interval of convergence is -1 to 1. The radius of convergence is 1. So just like it was back here, same idea. So the only difference is that this is now, we're thinking of this as a function. And our whole goal is going to be to represent functions as power series. That's our goal. So this is our first one. We now have a function that we've written as a power series. First one. We're going to have 12. All right, so a general power series looks like that. It's just a Taylor polynomial that goes on forever. So it's got an infinite number of terms. This one is centered at a and not 0. The one that I just had on the board here, the center of this is 0, right? Because it's x and x squared and x cubed. It's not x minus something. So the center is always obvious by looking at these x's. Whatever, if there's something being subtracted or added to it, that indicates what the center is. So that's the generalization there. The c sub k's are coefficients. And those coefficients you already know how to find because this is just a Taylor polynomial extended. So that's just the derivative of the function evaluated at the center divided by n factorial or k factorial, whatever the letter is. Okay, so c sub k's are the coefficients. A is the center, like we've already seen. And here is a picture of what happens with a typical power series. Typical power series is going to converge on an interval that's symmetric about the center. The radius of convergence, of course, is half the length of the interval. And we talked about it being a radius because if you allowed imaginary numbers in here, then you'd be on the complex plane, and all these complex numbers in here would be numbers that if you plug in there for the x, you would get convergent series. We're not dealing with complex numbers, but it's an obvious question. Why are they using the word radius? You never talked about a radius of an interval in your life. And the reason they call it a radius is because it's actually from the complex circle. But we'll be just looking at reals, so we don't have to worry about it. So that's what you should have in your mind. You've got a power series, which is an infinite polynomial with a bunch of coefficients. Most power series, if you grab a power series, most power series can't be rewritten as cosine sine e to the x natural log x. Most power series have a non-pattern to the c sub k's. The coefficients are just random. We are going to see, just like this one, that these coefficients are super prescriptive, right? They're all 1. The power series that are going to equal common functions will have little formulas for the coefficients that are very systematic. But if you just have no pattern to your coefficients, there's no way that that power series is going to be representing a common function. It's just an infinite polynomial.
So, is it kind of when we're talking about like within the common functions, and like the ones that we're doing in this class that are like have these patterns? It's a very small portion of all of them.
Right. So 99% of the power series will not have a common function representation. But the only way we get comfortable dealing with the concept of a power series is to deal with that subset that does have common function representation. So it's just like the real numbers and the irrationals. You never even were introduced to irrational numbers until kind of later. First, you're dealing with integer coefficients, and then rational coefficients, and then finally you get to irrationals. But it's that same idea. Rationals, any number you pick off the number line, 99% of the time it's irrational. Yet we are going to do most of our work with rationals. Same idea with power series. Most of the power series we work with, well, all the ones we work with in here, are going to have nice patterned coefficients, which will lead us to common functions. Okay, so let's take a look at how we talk about convergence. So for a power series, there's 3 possibilities. One is that it doesn't matter what x you plug in. Every x that you plug into the power series will generate a convergent infinite series. E to the x is a classic one. It doesn't matter what x value you plug in. It is going to match the function exactly. Some power series have a radius of convergence of 0. Every power series will converge at its center. And that's what we're talking about here. So can you visualize this? If you plug in A for x, that's the center, you're going to get C sub what? If you plug in x equals A,
C sub A.
you're going to get C sub. So if we were to write this out, this would be C sub 0 plus C sub 1 times x minus a to the 1 plus C sub 2, x minus a to the 2, etc. What happens if we plug in an A? What do we get?
C sub A? No.
Think again. Try again. Think about plugging in an A. If you plug in an A here, what do you get? 0. Plug in an A here, what do you get?
0.
What about there? C sub 0. So if you plug in A, all the terms are going to turn into 0 except C sub 0.
Oh.
So every power series will converge at its center because when you plug in the center value for x, everything disappears except for C sub 0. So every power series converges at its center. And this statement here is saying some power series only converge for their center, which would be a horrible power. It's not going to be a very valuable power series if it only converges for its center. Ari?
For the first one, where it converges for all of x, doesn't that mean you can choose any center?
It does.
It
Yep.
matters.
And so that's a good point. So when we're imagining a function that we're trying to approximate, if we are curious about what the function value is, say over here, if you have your center here, it's going to take a certain number of terms for it to get accurate all the way over here. But if you know that it's convergent for all x, you can pick your center as close as you want, and then you go out less far in the power series to get that same accuracy. So the further you are from your center, the more terms in the power series you're going to need to get accuracy of a certain level. Carter?
So all the functions in that, or all the series in that cloud, do they all converge at 0, or just the ones that we're working?
They all converge at their center.
Okay.
So
Yeah, they're centers.
at their center. So if the center is 0, then they converge at 0.
Okay, so that's a
Universal.
there's no deviation from every single power series converging at their center.
Correct. Every power series converges at least for its center.
But that doesn't necessarily make it useful.
It's not useful. If it's only convergent at its center, it's not useful. Right. We need it to be able to do more than that for it to be useful. Now here is the case that is the more common case that we're going to see. It takes a little more work. Here the radius of convergence is positive. It's some positive number. And so this says that x minus a, an absolute value less than r, will have convergence. And x minus r, an absolute value greater than r, is going to have divergence. So converges if it's less than r, diverges if it's greater than r. Kind of like the geometric series. Less than r in magnitude is going to converge. Greater than r, it's going to diverge.
What if it is r?
So on the boundary, things can be weird. So if you have your interval of convergence, and you've got your two boundary points, it's possible that you have no convergence, both converge, one diverge. You can have all options. So endpoints are always going to be tested separately. So this always is going to tell us that if you're inside the interval, so if you're interior to the interval, you have convergence. If you're exterior to the interval, you have divergence. And if you're right at the endpoints, you have to test them.
And if you were to allow imaginary numbers, you would have to test literally every point? Or is there some pattern?
If you are dealing in the complex numbers, your boundary has an infinite number of terms, an infinite number of points, so you'd have to, all sorts of strange things can happen on the boundary. Can converge for some, diverge for others. There may be a pattern, there may not be.
Is that why they call it complex?
Maybe. That's a good one. It is complex. Okay, so just kind of a little summary. This theorem implies that the interval of convergence is symmetric about the center of the series, so we've talked about that. Whatever the center is, the interval of convergence has to be symmetric about that. It's like a teeter-totter. It's got to be centered right at that center. Now, how do we figure out the radius of convergence? So are the two ways that we are going to use root and ratio. So that's why those two tests are going to be kind of the most important too, because they are going to be applied. They're the only two that we're going to use in this chapter. So here is what I was just getting at a moment ago. If your radius of convergence is 2 and your center is 4, you have 4 different possibilities for your interval of convergence. No convergence at endpoints, convergence at both, convergence at 1. So the radius, there's 4 options for any fixed radius. We always have to test those two endpoints separately, which we will get into, of course. All right, so the first thing we do is apply the ratio test. So we've got our power series. We're looking at it, we're like, oh gosh, where's it converge? We use the ratio test or the root test. Most of the time the ratio test is usually better, not always. And then we have our 3 choices here. the radius is infinite, which means that convergence is everywhere. The radius is 0, which means the convergence is only at the center. Or you have a positive radius of convergence that's finite, then you build this interval, and then you have to test the endpoints. That is going to be the one that involves the most work. Are we ready for work? Woo. It's Tuesday.
Yeah.
We just had a weekend. We're ready for work. Yay, we're ready. We're ready.
It's Monday, just kidding.
It's not Monday, is it? No. This day's better than Monday. So here is our first power series. There is a power series. Infinite polynomial. Usually with the power series, you're just going to say, okay, let's go with the ratio test. This one in particular, you see that factorial, so you would never even consider doing the root test. So if you see a factorial, we're always going ratio for sure. So the ratio test. So the ratio test, remember, we're going to take the limit as k goes to infinity of ratio is the, by ratio we mean the ratio of consecutive terms. So we're going to take a sub k plus 1 divided by a sub k, all in absolute value, so we are in fact finding absolute convergence. So this whole thing is a sub k. That's a sub k. So let's see what happens. Let's see what happens. So we're going to take the limit as k goes to infinity. A sub k plus 1, absolute value. All right, so k plus 1. So x minus 1 to the k plus 1 divided by k plus 1 factorial multiplied by, so we need the absolute value. We have an x in there. With our series of numbers, we often just had to get rid of the switch. That's totally off here, though, because x can be anything. It's a real number. So, you know, x could be 0, and then 0 minus 1 is negative. We need the absolute value. So absolute values have to stay here. Now we're going to flip the a sub k, so we'll get a k factorial divided by x minus 1 to the k. So there is our setup for the ratio test. And we'll have a lot of similarity to what we've already done with these factorials. How do these two factorials simplify? K plus 1 in the denominator? Because k plus 1 factorial, remember this could be written as k plus 1 times k factorial. So those two k factorials will cancel. So we're going to be left with just a k plus 1 in the bottom for that part. Now the numerator on the left, x minus 1 to the k plus 1. Down here we have an x minus 1 to the k, so we end up with just one factor of x minus 1. Now that still has an x in it, so that has to have an absolute value around it. K plus 1, k is a positive integer. Don't need an absolute value. So now we have the limit as k goes to infinity. Is there a k in the numerator? No k. That means that numerator is constant with respect to k. It does not change regardless of k. It's independent of k. So we have this scenario now. And what is the limit as k goes to infinity of 1 over k plus 1? 0. So we end up with absolute x minus 1 times 0. That's 0. Doesn't matter what x is. You multiply x minus 1 times 0, you're going to get 0. No matter what.
So it only converges at 1?
Well, let's go back in time and think about the ratio test. When you do the ratio, we called it R back in the prior chapter, when you found your R value, what was the conclusion?
If it was
less than 1 and converge. Is this less than 1?
Yeah.
This is less than 1, therefore converge for all x. All right, that's always less than 1. So the ratio test is generating a number, 0, for every possible x, which means it doesn't matter what x you plug in, the limit of the ratio is always going to be less than 1, therefore it converges for all x. So therefore you would write I, the interval of convergence, in interval notation like this, and therefore the radius of convergence is in fact infinite. The radius of convergence is always half the interval. So infinity, 2 infinity divided by 2 is infinity.
Do we have to say both for points?
You will be asked for both.
Okay.
You will be asked for both r and I. Okay, so this is one of those special cases where it converges no matter what the x is. So it's going to converge for all the x's. Now let's take a look at this one. So once again, we have a factorial there. So we certainly are going to go ratio test. And again, ratio test is going to be the limit as k goes to infinity of the ratio of consecutive terms. So we're going to do the same type of thing. We're going to look inside and find a sub k. Okay, there's a sub k. Now we're going to replace the k with k plus 1. So that's going to be k. Oh, this one we can actually do the fraction straight up. So k plus 1 factorial times x minus 10 raised to the k plus 1, all divided by k factorial times x minus 10 to the k. So that's a sub k plus 1 over a sub k, all in absolute values. Focusing on the k plus 1 factorial and the k factorial, what does that reduce to? K plus 1. Don't need the absolute value even, because that's positive. K is a positive integer. And the other part simplifies to x minus 10, just to the first power. That does need an absolute value, because x is an integer, a real number, positive real, negative real, whatever, any real. Once again, the x minus 10 factor, there is no k in that. If there is no k in there, then it can be factored right out of the limit. Now we can evaluate that limit. And what do we get? Infinity. When is this less than 1? Never. So therefore, the radius of convergence is 0, and therefore the interval of convergence is not really an interval. I mean, we write it that way. It's a set that contains just one number, namely the center of the series. Right? When you plug in x equals 10, everything disappears except for the 0th term. When k is 0, x minus 10 to the 0 is 1, so when k is 0, that's we get it all reducing down to just one constant value. So this is the other extreme. So these are the two extremes. All reals or just the center. But it's very easy to have, get your signals crisscrossed, because when this limit is infinity, you have a 0 radius of convergence, and when this limit is 0, you have an infinite radius of convergence. So you have to remember the ratio test. The ratio test says you have convergence when the ratio is less than 1. And so when you get a 0, that's less than 1, so you have an infinite radius of convergence. And when your limit is infinity, that's never less than 1. So the only value for which the series converges is the center of the series. And the center of the series is always right, whatever is being subtracted from x. That's the center. Okay? Any questions on the simplification? Conclusions? All right. Let's see. Let's go to the next page. Yeah, let's do this one. And we'll take our break after this one. So, once again, power series, and the question is, well, what are the x's for which this converges? Is it all x's? Is it some x's? Is it only the center? What's the center of that series? 0, because it's x minus nothing, right? There's just an x.
So there's a switch.
It is an alternating sort of series. It would be alternating depending on what x is.
So do we take that switch out or no?
Well, with our ratio and root test, we do absolute value, so the absolute value will take it away when we do the limit. But when we do the limit of either the kth root or the ratio.
But we should do the ratio test for this one, right, since we have k's and exponents.
We could use the root test.
Or
Do the root test. I thought that's what you meant. Let's go with the root test. So let's go with the root test on this one. So we're going to take the limit as k goes to infinity of the kth root of the absolute value of everything in here. And after you've done a couple of these, there's no reason that you'll ever write the switch again in here, because you're going to take the absolute value, so the switch just goes away anyway. So this will be limit of, so the absolute value is going to wipe out the -1 to the k. The kth root is going to wipe out the power on the x and the power on the 5. So we are going to be left with this.
What?
Kth root of x to the k is x. Kth root of 5 to the k is 5. But we have an absolute value in there. X could be negative. We want to make sure that we're turning everything positive, so those absolute value bars have to stay on the x. Don't need them on the 5 because 5 is positive. The -1 to the k goes away. It's either +1 or -1. Absolute value makes it +1. Okay. The root test has the same conclusion as the ratio test. We want to know, when is this? Oh, let's do the limit first. What is the limit of that? This is as k goes to infinity.
Absolute value.
It's just that. There's no k. No k. That means that this is constant with respect to k. Constant with respect to k. So this is what we have. Right? There's no k in there. Constant with respect to k. So what is the ratio test conclusion? We have convergence if the limit of the kth root is less than 1? Less than 1? So we want to ask this question. Now we're in that more ambiguous case. We didn't get 0, we didn't get infinity. Some x's are going to create a ratio, a root that's less than 1. Some x's won't. Right? If x is 10, not less than 1. If x is 3, less than 1. So this has some more nuance to it. We multiply both sides by 5. And if you want to visualize this, this says, oh, we are going to have convergence anywhere inside the interval. Right? From there to there. Our center is right here at 0. All the purple dots, we have convergence. So we know the goalposts, if you will, for the interval of convergence. We know that it's going to go from -5 to 5, but we don't know yet whether we have a bracket or a parenthesis on each end.
Oh, so we have
Now we test.
the end.
Now we go back to chapter 10. So chapter 10, we test. So we're going to test x equals -5. So we're plugging in -5 into this series. And when you're doing these tests, you can ignore the k piece, the 0 to infinity. It does not matter. It's an infinite series. So we're plugging in -5 to the k, 5 to the k. So we want to know, does that infinite series converge or diverge? That's what we want to know. Well, we first can peel off that switch. There's kind of two switches, aren't there? There's the -1 to the k, but then in here there's a -1 to the k. And then we have a 5 to the k over 5 to the k. What is -1 to the k times -1 to the k? Which is
1.
1.
Always 1.
Right? So this whole part right here just vanishes. This becomes 1.
And 5 to the k and 5 to the k are equal, so that just.
Okay, so this all simplifies to that. And does that converge or diverge? We have one of each so far.
Is it a trick question?
No, it's not a trick question.
It's just 1.
What does this mean? It means 1 added over and over and over and over and over, right?
Oh, so.
It's 1 plus 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 1. So this diverges by which test? The divergence test. Right? The limit of a sub k is the limit of 1, which is not equal to 0. All right, so at -5 we have divergence, which means we put a parenthesis on the -5 for I. -5 is not included. Let's test the other endpoint. So now let's test x equals 5.
Oh, would that just be a switch?
So now we do have a switch. And we're going to have 5 to the k over 5 to the k. Fever dream. So we have that.
But that's -1 plus 1 plus -1 plus 1, which is 1/2, right?
So it converges, right?
Wait, it's 0?
It's also 1, and it's also -1.
So this one starts at 0 if we go back up here. So this is what the expansion is going to look like.
If you did that out to infinity, would it stay 0?
So the only way a series converges is if the partial sums approach a single number. Let's take a look at the partial sums.
You
What's the
approach
first
3
partial
numbers.
sum? 1. The second partial sum is 0. The third partial sum is this sequence, so the sequence of partial sums, does this sequence approach a single number? No. This diverges. So you can say that this diverges by divergence test because the limit as k goes to infinity of -1 to the k does not exist. All right, it's just wobbling around. Dunk, 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 dunk. Wobbling. So we exclude both endpoints. So here is our interval of convergence. -5 to 5, excluding endpoints.
So then, how do you say the radius?
So the radius is 5. So the radius will be 5 regardless of what is happening at the endpoints. And so we actually can identify the radius first. As soon as you have your absolute value of x isolated, this is always going to be the radius right there. As soon as you have absolute value of x isolated, that is going to be the radius. When you look over here, you can tell, right, that half of this is 5. This distance from the left endpoint to the right endpoint is 10. 10 divided by 5 is Or 10 divided by 2 is 5.
But it doesn't touch.
Right. So when we say the radius is 5, we mean that it can exclude or include that endpoint.
Oh, okay.
So the radius just gets us to the endpoint, but doesn't tell us whether we include it or exclude it. That's why we have to do more than just the radius.
I'm good.
Okay, let's go for a break. Let's go take a break, 10-minute break. I'll go get my phone so I can log on to the Dane computer.
There's
So at this moment, we are staring at e to the x. That's the function, the black function, this curve. There's e to the x. And that purple line is the tangent line at 0. And as we increase, there's the second order Taylor polynomial. You can see that it matches e to the x in a wider range, wider interval. And then as we keep creeping, here's the third order. It matches it better and better. And the further, why does that keep coming up? And the further out that we go, there's the fourth order. Now, notice that the match seems faster on the right. So, for example, if you wanted to get an estimate of e to the 1/2 with a Taylor polynomial centered at 0, it's pretty good already right over here. It's not quite as good if we go half to this side. Pretty good though, but then it starts, spreading off there. And then as we go further and further out, it just wraps around the curve, and it will do that, and it will do that, and it will match this function exactly. So now you can see that on the right, it's matching really, really, really good right away. But here, if we want to get a match out in this region, we're going to have to go way out. This one only goes out to 20, piece of 20. And we're not even close to matching at -10 yet.
But if you got a piece of, like.
So if we go out to
30
piece
billion or something.
of 50 will match. But what the better thing to do is to, if we wanted to match at -10, if we moved our center, right, we could move our center over, and that would be the easiest way if we centered it, let's just say 8, or whatever I typed in. Yep, I wanted center at negative, so that has to be a plus. So if I want it over that way, now, it's still not matching very good at 10 though, is it? I feel like I goofed up my shift somehow though. Because if -9 is the center, I didn't build it right. But you get the idea though. If you made the center not -9 and created the proper coefficients, it would match over near -9. So let's take a look at inverse tangent. So here's inverse tangent. And turn off that one, turn on this one. So inverse tangent, there's the thing that you found many times, the tangent line for inverse tangent right there. And as we start to go out, inverse tangent, oh, interesting, right? This one is only going to have a radius of convergence of 1. And this is one of those things I was talking about that's really weird. Because when you look at this function for arctan, you're like, dang, that's a nice, smooth function. You can take derivatives of every order. It's infinitely differentiable. Or at least it has tangent lines everywhere. Looks like it's infinitely differentiable, right? So it feels like you should be able to build a Taylor series that matches it all the way out. But there's one thing that's fishy with inverse tangent. What is the derivative of inverse tangent? 1 over 1 plus x squared. So the derivative is 1 over 1 plus x squared. Okay, that's differentiable, and you could imagine continuing to take derivatives. Okay. How about the, how am I going to back into this? Okay, I'm going to back into it this way. So this is our geometric series. We already looked at the power series for the geometric series. Oh, you know what I'm going to do? I'm going to do it this way. I'm going to do it this way. I'm going to do it this way. This is a better way to do it. Let's go to these series down here. I've got the main 12 power series that we are going to study on this page here. So let's do this. This will give us a better way to get at it. Okay, geometric series, right there. Interval -1 to 1. And if you graph that function, if you graph the 1 over 1 minus x, everyone, I hope, is good with graphs. Right, we all know that this is a shifted hyperbola by now, I hope. Right? And then the center of the graph is at x equals 1. So the center is right here. Right? That's where that asymptote is. So keep that in your mind. So this graph, this power series is centered at 0, right? So that power series is centered at 0, and the distance over to this asymptote is 1 unit. And this is one of those things that I alluded to, that the interval of convergence is going to be from -1 to 1. So if this is our center at 0, right, we get to this asymptote, it's 1 unit away. Our radius of convergence is 1. The interval is going to go from -1 to 2. -1 to 1, 2 units wide. So it knows that this asymptote is 1 unit away from the center, which it's not going to allow it to get any closer over on this side. The interval is going to stop 1 unit in the other direction also. All right, so just keep that in your mind. So we've got that interval for 1 over 1 minus x. Now let's go to this one down here. So once you have one power series, you can get another power series by replacing all the x's with something. So here, I'm going to call this one the alternating harmonic. And we find it by taking the x up here and replacing with -x. We are going to have the same interval of convergence. This is also a hyperbola, and the center of the power series is 1 unit from the asymptote. Okay? All right. So that seems simple enough. Take that one, replace all the x's with -x. It becomes an alternating harmonic. So there we have it. Now, so keep that one in your mind. Now let's come down to inverse tangent. Tell me how to get to inverse tangent from this. What would I need to replace that x with to do some math to get to inverse tangent? So if we replace the x with x squared in the alternating geometric, we would have this power series for, we don't know how that happened. So if we replace the x right there with x squared, we'd have 1 over 1 plus x squared equals, replace this x with x squared also on the far right here. That one starts at 0. That stays the same. Replace the x with x squared. That becomes x to the 2k. We'll talk about the interval of convergence in a minute. So that is the new power series for 1 over 1 plus x squared. New power series. How do we get to arctan from that? Integrate. Right? If you integrate 1 over 1 plus x squared, you get arctan. This is just a polynomial, so you can integrate it. Add 1 to the exponent, divide by the new exponent. That is what builds this. Now let's look at the interval of convergence for a minute. So the interval here is -1 to 1. If we replace x with x squared, here's how we get the new interval of convergence. So for this series, this was the interval of convergence, -1 to 1. If we replace the x with x squared, we then solve this inequality for x. We're going to talk about how to do that in a minute. Just trust me at this moment that it's going to end up being that. We'll talk about why, but that's going to be the solution. So the interval of convergence here is also going to be -1 to 1. Then when we integrate this power series, we get to arctan. Arctan, whenever you integrate a power series, you may increase convergence at the endpoints. You can't change the guts. You can't change the middle. You can't change the interior. But you might gain convergence at the endpoints when you integrate a power series. It turns out, and again, we'll look at why later, but the interval of convergence for arctan is -1 to 1, which we just saw on that visual on the board, which felt weird because it looks like you should be able to build an infinite polynomial for arctan for all x. But what happens is that this is the source to get to arctan. So somehow in the math, which I don't understand, somehow in the math, it knows that this has an interval of convergence of 1, and that we started there to get to this. And to get to this, we use that to get to this. And you cannot create an interval of convergence that gains measurably. All it can do is gain at the endpoints. So even though that arctan function is super smooth, has infinite derivatives, we cannot build an infinite polynomial that matches more than just on that interval.
Didn't we use alternating harmonic?
We started with the harmonic, and then we went to the alternating harmonic, and then we made a replacement in the alternating harmonic, and then we did an integration.
That's the harmonic.
Did I say harmonic?
You said harmonic.
I mean, it looks like the harmonic. Or geometric. Geometric. Thank you. Yeah, it's that harmonic. Geometric. This one is geometric. This one is alternate. Did I say alternating harmonic?
Yes.
Alternating geometric. Alternating geometric. Geometric, alternating geometric. And then we integrate the alternating geometric after we replace x with x squared. So somehow in the math, it knows that somewhere in the chain of derivatives and integrals, there's only one unit to an asymptote. And it preserves that interval of convergence, at least the inside, all the way through. Which is, again, I don't understand how it does that, but it does it. So when we look at these power series, once you have one power series, you can build a whole bunch. So for example, to get from the geometric, we can integrate. And if we integrate the left-hand side, we get this function. Integrate the right-hand side, it's a polynomial, so you just integrate term by term. So all we have to do here is add 1 to the exponent, divide by the new exponent, and then I re-indexed it so that it was an x to the k and not an x to the k plus 1. So that is the power series for that function. There's its interval of convergence. Here we gained. And so a lot of times when you integrate, you can gain at endpoints. So when we integrate from here to here, we gained 1 extra point of convergence, the left endpoint. And then we talked about getting to the alternating geometric. If you integrate the alternating geometric, you get another power series. This one gains convergence at the right endpoint. And now here, natural log is a function we see all the time. But we can't create a power series for natural log with a center of 0 because natural log is not defined at 0. So what we do to come up with a power series for the natural log function is that we build this one for natural log of 1 plus x by integrating, and then we're going to replace the x with x minus 1. So if we replace all these x's with x minus 1, we'll have a new power series, and it will be for natural log of x. That's going to be its interval of convergence. And if you think about the natural log function, if you center your power series at 1, it's 1 unit over to that nearest asymptote. Right? Natural log has an asymptote at 0. So if you center your power series at 1, the interval of convergence is going to be from 0 to 2. 1 unit in radius. And then there's arctan. While we're looking at these, let's just look at the next 6. So the first 6 are totally based on the geometric series. You already know that power series. It's what we did in the last chapter. The next 6 are based on the exponential function. There's the power series for the exponential function. Second most important power series. Now let's look at sine and cosine here. This should be the first time you've ever seen a connection between e to the x and sine and cosine. Look at the terms. Isn't sine just the odd powers of e to the x with a switch thrown in? Right? So if you know the power series for e to the x, you know the power series for sine and cosine. Cosine is the even powers with a switch thrown in.
I thought the first time we saw a connection was with integration by parts.
Did we see an integration by parts? How e to the x and sine were connected?
Because they're both integrated.
Oh, they both had those circular derivatives.
Yeah, so those are like.
But we weren't writing e to the x like as, we weren't seeing sine as part of e to the x. We were seeing that it had a similar property, that its derivatives were circular.
So the way we could rewrite e to the x and turn it into a sine function is that?
We'll talk about it. It's similar. We have to throw an I in there. But we'll at this stage, just notice that sine is the odd pieces of e to the x with a switch thrown in. Cosine is an even, are the evens.
I'm assuming this is where
Easy to remember because sine is an odd function, cosine is an even function. Right? Cosine is symmetric about the y-axis, so it just grabs all the evens. Sine is symmetric about the origin, it's an odd function, so we just grab all the odds.
assuming this is where the e to the pi
Yes.
plus 1 thing comes from?
Yes. E to the pi I plus 1 is 0, most important formula in all of math, yes. And now notice the hyperbolics. Remember that when we did the hyperbolics, you could write the hyperbolics, the cosh of x was e to the x plus e to the minus x over 2. It was the average. Well, now you can see exactly why. Sinh and cosh are exactly the odd and even terms of e to the x. So this one you can write directly. Right? You can write e to the x is equal to this plus this divided by 2.
Why is there a subtraction and an addition for the very first terms when we switch?
Yeah, up here?
Yeah, so there's like x minus and then it's the term. So it's 1 minus and then it's the rest of the term.
Here?
Yeah.
This is alternating though, right?
Yes, yes, yes. But
It's
like,
alternating.
Are they related to the e to the x? The initial one? Is that one?
So the only thing with e to the x, the terms are going to match in magnitude, but we're going to have every other one's going to be negative. And then for sine, same thing. It's going to match all the odds, except every other odd will be negative. It's going to match exactly for sinh and cosh, though. And notice, so cosh and cosine, identical, except for the pluses and minuses on cosine. And then we'll get to binomial series. That one's going to be all by itself, weird. Okay, so let's go back to here. We're on that page. All right, so little side note on all that stuff. So that's how Taylor polynomials work. Interval of convergence is kind of subtle. Sometimes it's really mysterious how it knows what it should be.
That's great.
Okay, here we have a power series. It's got a switch in it. As soon as it has a switch, we know that that's just going to go away whether we use root or ratio test because we always take an absolute value. And what do you want to use here, root or ratio? Root's going to be a pain because we have to take the kth root of the square root of k.
Oh, yeah.
So we're going to go, let's go with ratio. So we're going to do limit as k goes to infinity. And again, at this stage of the game, let's just not even write the switch in here. Because we know we're taking its absolute value, so it's going away. So we're going to have an x to the k plus 1 over the square root of k plus 1. We divide by a sub k, which means multiply by the reciprocal, which means this. And let's not even put the switch in because we're taking the absolute value. Switch gone. Okay. How many x's and where?
The ones in the
1 in the numerator, 1 up top. It does not have a k in it, so it can come all the way out to the front as absolute x. There's no k in that x. So it doesn't depend on k, so it doesn't affect the limit. And then we have the limit of square root k over k plus 1. And here's where we can use a multitude of concepts. We can say, oh, polynomials. We can just ditch the 1 because the polynomial is dominated by its highest power. Then k over k is 1. What is the overall, what is the limit of just this limit part with the k over k plus 1s? So it's just going to be square root of 1, which is 1. And then we have it multiplied by absolute x. So you can do the L'Hopital rule on the inside. You can divide by the highest power k. You can get rid of the non-consequential terms. Many ways. Now with the limit, what does the limit have to be for convergence? What does the value have to be? It's got to be less than 1, right? This is ratio test. So we want to know, hey, when's that less than 1? Well, we already have the absolute value of x isolated here. We don't have to divide by anything. This tells us right away that the radius of convergence is 1. Whatever this number is on the right, once you isolate the absolute value expression, that's going to be the radius. Your interval of convergence, let's see, we know the goalposts. We know it's going to go from -1 to 1. But we don't know what happens at those two endpoints yet. We have to test. We have to test the two endpoints. So let's go ahead and test x equals -1. All right, so we go to our series. We're going to plug in -1. So we have -1 to the k divided by square root of k. What happens with these -1 to the k's? They simplify to 1. -1 to the k times -1 to the k is -1 to the 2k, which is 1. What kind of series is that?
P series,
What is the value of p?
1/2.
So p equals 1/2. That's less than 1. Therefore, converge or diverge? Diverge. So that tells us -1 is excluded, so we use a parenthesis on the left. Now we've got to test the other one. So let's see, does this change much? We have -1 to the 1, -1 to the k. Plugging in a 1, 1 to the k is just 1, so we have this. So now we have an alternating series. And does that converge or diverge? Converge or diverge? Converge. So the limit of a sub k is 0. 1 over square root of k, limit is 0. And it's decreasing. Right? 1 over k decreases. 1 over 5 is bigger than 1 over 6 square rooted, is bigger than 1 over 7 square rooted, and it's decreasing in value. Now, back in chapter 10, you would have to show this using the alternating series test. In this chapter, when you're evaluating endpoints, it's enough to say by alternating series. You don't have to go into the details. But you should at this point be able to see why. Right? The limit of this is 0. And the terms are decreasing because as you increase this k, the denominator is getting bigger, so the fractions are getting smaller. So it's okay in chapter 11 to just say that. If it's alternating and the denominator is getting bigger, you know the values are getting smaller in magnitude. So you know that it's decreasing to 0.
So on the test, like we can, when we're working with these on the test, we can do just say that. And
Yeah,
that's okay.
that's
If you
totally-
specifically ask us to do a problem with the alternating series, you want us to actually do it.
Right, exactly. So the chapter 10 stuff, it will say, use the alternating series test to show convergence or divergence. here, when you have to test endpoints, this is just a small teeny piece of a huge problem. You can just say that. Yeah. So we're going to include that. So there is our interval of convergence, along with our radius of convergence. All right, so here's where we get into some really subtle stuff in this part of the section. Namely, well, I'll show you as we go. So here we've got two power series. They both converge, one to F, one to G. If you add or subtract on their interval of convergence, you'll still have convergence. So you've got two power series that converge. If you add them, you have a new convergent power series. If you subtract them, new convergent power series. Okay, next one. We've got a convergent power series, and we multiply by a power of x. So we're going to multiply by a power of x. That power of x can be moved inside, and it is not going to change the interval of convergence other than in one subtle way. So the interval of convergence, it's still I. We still have the same I, but we say this: the series converges to that quantity for all x not equal to 0. This is not going to come to play in this book, but let me just explain why they have this funny not equal to 0 business. The k plus m has to be bigger than or equal to 0. When you have a polynomial, the exponent is a non-negative integer. Right? You can't have a -1, a -2, a -3. It's not a polynomial. Right? 1 over x squared is not a polynomial. So the power on these x's here have to be non-negative integers. Theoretically, if this is, say, x to the k, theoretically, this m could be negative as long as k plus m is greater than or equal to 0, it's fine. But it's possible that this is like x to the -1. So then you have an x in the denominator, and x can't be 0. So all they're doing by this is saying we're just, making room for the possibility that this power series is being multiplied by something that has division in the denominator, division by 0 in the denominator. It's not going to come to play for us. When we multiply by a power of x, I haven't seen a single example in the book where they do multiply by like 1 over x, so I don't know why they call this out. All the powers of x that we're going to multiply by are x to the 3, x to the 5, x to the 7. So you just put it to the inside, and you don't even have to worry about this because you're never dividing by 0. So that's why it's there, just in case. The next one is pretty straightforward. The next one says if you do a substitution, so we've got a power series that converges, and we are going to substitute, instead of having f of x, we're going to take another function and put it inside of f. So we're doing a composition. The new power series is going to converge as long as that substitution that you made is in the interval of convergence. So normally our power series converges when x is in the interval of convergence. If you replace the x with h of x, well then for it to still converge, h of x has to be in the interval of convergence.
The value or its convergence?
Its value.
Okay.
So if the interval of convergence goes from -1 to 1, then h of x's values must be between -1 and 1 for convergence. I'll show you how. We'll do an example. Very simple. Okay, so here is the geometric series. Geometric series, not the harmonic. It's the geometric. Geometric. So we want a power series for this function. Isn't this just x cubed multiplied by the power series for 1 over 1 minus x?
Yes.
Yeah, that's all it is. So here's our geometric series. 1 over 1 minus x, there it is. We multiply by x cubed, so this is what I was just talking about. There's no division by 0. We don't have to worry. All we have to do is come right in, add that up. K goes 0 to infinity. And the interval of convergence is not going to change. We don't have to do anything different. Interval of convergence will be the same. All right, so that's all that we do. Now for this one, this is part C, composition. So here, instead of 1 minus x in the denominator, we take the x and we're taking x cubed and we're putting it in for the x. So this is going to be the infinite series notation. I'm going to start shorthanding. It gets old writing on all of these, 0 to infinity. If you just put a 0 there, it's understood it's k equals 0 and it goes to infinity.
Can we do that on the test?
Yes, you can do that on the test. So here, all we are going to do is come in for our infinite series for the geometric, and we're replacing x with x cubed. So we're replacing this x that we see right there, that x gets replaced with x cubed. So inside this summation, there is our new power series. K goes from 0 to infinity. Yeah, you can use that abbreviated shortcut, totally fine. It's obvious that that's for k. K starts at 0. Now, here is what I mean when I say we have to replace the x with h of x. Normally, here is our interval of convergence. This is where it started. But then we replaced x with x cubed. So that means we also have to replace the x with x cubed in the interval of convergence. So that's what it means when it says h of x is in I. We take the x, replace it with h of x. H of x in this case is x cubed.
How are you able to rewrite 1 over 1 minus x cubed to be just x cubed?
Say that again?
How are you able to rewrite 1 over 1 minus x cubed to just be x cubed?
We're writing it as an infinite series. We're replacing the x here with x cubed. So this is the power series for just an x being down here. So if we replace this x right here with x cubed, right? This x cubed is replacing this x, so then we also replace this x with x cubed. So to get, for this to match this, we replace the x with x cubed. So for this to match this, we also replace the x in there with x cubed. So we just do the same thing for every x. And in fact, we also do that over here with the interval of convergence. And then we just have to solve this inequality, so we take the cubed root of everything. Oh, nothing changed, right? We still end up with the same interval of convergence.
How could you split the absolute value of x into x?
How to split this into this? That's what this means from back in algebra. The absolute value of x less than 1 means all x that are within 1 of the origin. Right? That's what that means. This is a compound inequality. X is less than 1 and greater than negative 1. Gage?
What if it was x squared? Because it's
We'll get to that one very soon.
Yay, I! Gotta love
Yeah,
my brain.
no eyes,
Oh, come on.
but we'll get to that one because that one's a little subtler, if that's a word.
More subtle.
More subtle.
Your wife would correct you on that
I'm sure she would. She's great at that. She's a pro. Okay. Now we have a power series for ln of 1 minus x. So we have a power series for ln of 1 minus x. We want a power series for g, which is just x squared times the power series for f. So this is just like the last page. So all we're doing is multiplying x squared by the power series for natural log of 1 minus x. The power series for natural log of 1 minus x is that. It starts at 1, so it looks like this. So once again, all we do is jump the x's into the summation. So we're going to end up with x to the k plus 2 divided by k, still starting at 1. And the interval of convergence will not change when all you do is multiply by a power of x. Interval of convergence stays the same. Don't have to check endpoints, don't have to do any funny business. No funny business. Okay, so similar to the last slide. Now we have an x up here that's being replaced with x to the 4th. So if we replace the x here with x to the 4th to create the corresponding power series, all we do is replace that x with x to the 4th. So the power series here is going to look like, it's going to start at 1. This x gets replaced with x to the 4th. And there it is. So we substituted x to the 4th in for x. And if we simplify those exponents, there's our power series. Now here's going to get to Gage's question.
So will we have to memorize all these different, like,
Those ones?
yeah.
You're going to have to memorize 4 power series, and I will tell you the 4 next week.
Oh, so not this week? Or?
Maybe Thursday.
What is our test?
Test is a week from Thursday. Yeah, so maybe I should tell you Thursday.
Thursday.
It's a week from Thursday, right? Next Thursday, yeah. We're in week 12. We only have 3 weeks left. Somehow, I can't even believe it. Okay. So here's where we have to be careful. So this is going to get at your question, Gage. So we replace x with x to the 4th. So we have to replace x with x to the 4th in this interval right there, and then solve that. Okay, so here is my approach for solving these. That's, I think, pretty simple. X to the 4th is never negative. This is always true, right? That's always true. It's always greater than or equal to -1. So you can just get rid of that. Right? That's always true. It doesn't matter. That's always true. We just really are focused on this side. Because that's always true, it's irrelevant. If it's true for any x in here, this is the side that matters. So what this means then is that for that to be true, what we say is, so here's the step that gets a little funny. So our conclusion is going to be this. That's going to be our conclusion. So what you can do is think in your mind, like when we do, if you want to think about graphing, here's one way to think about it. So one way to think about it is this. So we are graphing the function y equals x to the 4th. It looks like that. And we want to know when is it less than 1, greater than or equal to -1. So if we look at this graph right there, right, of course it's always bigger than -1, greater than or equal to -1. That part's always true. If we come over here to 1 and over here to -1, then right here we have an open circle and an open circle. Because we don't want to be equal to 1, we want to be less than 1. So this interval, open at -1, open at 1, that will be the interval that satisfies that. So you're thinking of these as functions. So if you want this function, either way, you can even be up here. X to the fourth is just this looking shape, parabolic-ish. There, we want the function values to be greater than or equal to -1, which of course they are, and less than 1. Well, if you plug in 1 or -1, you're at exactly 1, which is too much. So we want to go right up to, but not including the 1 and the -1. Okay. So this is our interval. So we actually lost a point, right? Because the original interval included -1, but now we're excluding -1.
So 2 things. One, formatting. Is it all right on the test if we only have like that one under there once? Or do we need it?
I should put it on all of them.
Okay. So on
Should
the
put
test,
you should put it on all of them, yeah.
should as in you probably should, or should as in I'll take points off?
I'll take points off if there's nothing there, because that's a little different in this context.
That's
There's
just,
some contexts where it doesn't matter, like when you're analyzing endpoints, it really doesn't matter because all we care about is that it converges or diverges.
Okay.
Here, where it's equal to a function, we need to be a little more careful because we have two sides of an equation. So this has to start at 1. It can't start at 2. When we write this, we're implying that it doesn't matter if it starts at 0, 5, 100. We only care about convergence or divergence. But here we're setting it equal to a function.
Okay.
So this has to start at 1. It can't start at some random other integer. It's got to start at 1.
And then I think I'm a little bit lost on how you went from the less than or equal to just
Yep.
less than.
Okay, so let's look at this inequality. Here, y equals x to the 4th is this right there. You agree?
Yeah.
So there's y equals x to the 4th. We want to know the x values that make it less than 1. So we want to know what are the x values for this parabolic looking thing.
Okay.
What are the x values that make its function values under 1 and above -1? Well, they're all above -1, right? The purple is...
So you don't have to worry about that.
So we don't have to worry about the -1 at all, which is why I took it off here. It doesn't matter, because
Okay,
it's
so you
always...
just drew it for like a visual. So what your final answer should be is like between what and what on the x-axis?
Yes.
Okay.
Right? Because we're trying to find the x's that satisfy this. So we're trying to find the x's for this purple that give us a purple value that's less than 1.
Okay.
How many questions are gonna be on the quiz?
I forget.
No.
You can find out. Look at the old
Quiz
ones.
only says 5.
Yeah, there's
Test.
quiz or exam.
The test, like the exam.
Yeah, I forget. It's gonna be enough to challenge you.
Is the
Look at the prior exams.
15
I'm asking, is the worksheet due this Thursday?
Yes, this Thursday.
Oh.
But it's not on chapter 11. It's only on chapter 10.
Oh, it's only.
It's only chapter 10.
Is there a chapter 11 worksheet?
No, the same way we've done it all semester. There's 2 chapters per unit, and the worksheet's always the first chapter. That's the pattern. It's a finite series. N equals 3.
That's my boardroom.
Okay, check this out. This is pretty
I
cool.
didn't put that chair there.
So I already alluded to this. If you have a power series, it's really just a glorified polynomial. So if you want to
Exactly.
take a derivative or take an integral, you just do it term by term. That's all you do. So all this says is, if you have a power series and it's differentiable, all you do is the regular derivative. Bring down the exponent, the k, subtract 1 from the exponent. That's how you differentiate a power series. It's a polynomial. Bring down the power, subtract 1. Same thing with the integral. You add 1 to the exponent, divide by the new exponent, but then of course you have a constant of integration because when you integrate a polynomial, you gain a constant. Now, the interval of convergence will not have the goalpost change. If it goes from -3 to 3, it's still going to go -3 to 3. But when you integrate or differentiate, you have to retest endpoints. Convergence or divergence can change if you take a derivative or an integral. They don't change if you multiply by a power of x. They don't change if you do certain things. But if you take a derivative or an integral, they can change. Usually if you differentiate, you lose convergence at endpoints. And usually if you integrate, you gain. Usually. Question?
Is that plus c within the sum or not?
No. There's only one c. If it was inside the sum, then you'd have an infinite number of c's.
But they would all be 1c.
Then they would combine. Then they combine to one c anyway. That's true.
So it could be inside or outside. That's weird.
So here is what we're talking about. So endpoints have to be tested separately. So again, frequently differentiating will lose convergence. Integration will gain convergence.
15.
Okay, so here is the hardest part of the chapter. Here's the hardest part. We have a function that we want a power series for. We just did some that were pretty easy. Multiply by a power of x, do a substitution. Here's the hard one. We want to get a power series for g, knowing the power series for f. F is the geometric. We've got the power series right there. We know it's interval of conversion. We are good with f. We've been doing that f type thing for almost 6 weeks. So we're good with that. How do we get to g from f is the question. Obviously, we're not just multiplying by a power of x. Obviously, we're not just substituting. We can't just turn this x into an x cubed. That doesn't give us this. So the last slide was all about derivatives and integrals. So we need to either differentiate or integrate that to get to that. What do you think we're going to do?
Differentiate.
Huh?
Differentiate.
Differentiate. Yes. Why wouldn't we integrate?
Because there's more powers there, and then if you integrate, then the powers would go away.
And if you integrate this in particular, you're going to get a log. You're not going to increase the power. So like Yanel said, if we differentiate a 1 over x, we bump the power up in the denominator. Derivative of 1 over x gives us a 1 over x squared with the minus sign in front. Yeah, exactly. All right, so let's do it. I'm just going to do what you said. Okay, so f of x equals, I'm going to write it in a more easily differentiable way. So there's f of x. The derivative of f, the first derivative, the minus comes down, we have the base staying the same, we subtract it from the exponent, and then chain rule says multiply by
Derivative of the inside.
derivative of the inside, that's a -1, so that becomes positive. All right, we're getting closer. This is a 2 in the denominator in the exponent position. So let's take one more derivative. We should be there. So -2 comes down, we subtract 1, and then multiply by -1 again. Ooh, we're so close. So this is equal to, move that down a little. So this is equal to 2 over 1 minus x
That's why.
cubed. Okay,
2g of x.
great. So this is equal to, so this is f double prime of x. Everybody agree with what Austin just said? This is 2g of x. Everyone agree? So if we isolate g, because we're curious, how do we get to g from f? So g is going to be 1/2 f double prime of x. That's how we're going to get to g from f. Okay, let's do it. So now we're going to do it in summation form. So f of x is this summation from 0 to infinity right there. F prime of x, all we do is take the derivative using the power rule. All right? Now first subtlety here with the derivative. So think about your polynomial here. If you differentiate it, what should the first term of the derivative be?
X, sorry, 1.
So when you take the derivative of 1, you get 0. The derivative of x is 1. So the first term of the derivative should be 1. And in order to make that happen, what do you think this index should start at? 1. Right? We shouldn't have an x in there. Right? If we were to keep our index starting at 0, wouldn't we have a division by x? We'd have, if we plug in a 0 for that k, we'd have x to the minus 1, which is 1 over x. That is not what a polynomial looks like. Polynomial always has to have an exponent greater than or equal to 0. And think about it. When you take a derivative, don't you lose a term if you've got the constant term present? Right? You lose a term, and that's what this is representing. We're losing a term.
So does the second derivative start at 2?
So let's take a look. So second derivative. So we bring down the k minus 1, subtract 1. And yeah, we can't start at 1 because then we'd have x to the negative 1, which is no longer a polynomial. So we lost the term, so that's going to bump up by 1. We're almost there before we have to do a ton of other stuff. Like test the endpoints. Okay, so g of x, now we're done with the power series part. It's going to be 1/2 summation starting at 2, k less 1, x to the k minus 2. So there, we now found a power series for g. Power series for g intact. The only thing we don't have yet is its interval of convergence. We differentiated twice, so we might have a change at the endpoints. Now, based on that rule of thumb that I gave you, that usually when you differentiate, usually you lose convergence, you don't gain it. So most likely we'll have the same interval. But we still have to test. You always have to test when you take a derivative. So we have x equals -1. That's going to be our first test. So we plug in -1 here. So we have 1/2. We don't even need the 1/2 really, right? Because convergence or divergence is not affected by a constant multiplication by 1/2. So we don't care about that 1/2. And here we don't care about whether we start at 2 or 5 or 10. We just care whether there is convergence or divergence. Whoops, -1. Okay. Do you see that this diverges? So the a sub k, we have k times k minus 1. And then this is this a switch? So if this starts at 2, we have a +1. And then 3 would be a -1. Then 4 would be a +1. Then 5 would be a -1. So this is a switch.
And you excluded the negative, and you excluded the 1/2 from here, right?
And we don't care about that 1/2. So if this is a switch, it's alternating. And with an alternating series, a sub k doesn't include the switch. And what's the limit of a sub k here? K times k minus 1? What's that limit as k goes to infinity? Infinity. So this diverges. So the limit of a sub k is the limit of k times k minus 1, which is equal to infinity, which is not 0, therefore diverge. So that's diverging by the divergence test. A sub k has to go to 0. If it doesn't, you have divergence automatically. And for an alternating series, a sub k is everything but the switch. That's your a sub k. All right, so we have divergence at one endpoint. Let's test the other endpoint. So if we test x equals +1, not much has changed. Not much has changed. We have k times k minus 1. And isn't positive 1 to any power just positive 1? So isn't the a sub k the same? Right? A sub k is the same. So this is same as above. So therefore, the interval of convergence has divergence at -1 and 1, and the interval is just going to go like that.
On the test, you wouldn't want us to like retest the same thing, like it has like the same conditions, I guess.
If it's the same a sub k, you don't have to rewrite the same exact thing again.
Okay.
You know, you can just say same a sub k as the other endpoint or something.
So when you differentiate or integrate, you can only change the endpoint, it's not the radius.
Yep. Yep. So differentiating and integrating, only the endpoints can possibly change. All right, let's at least start this thing. All right. So once again, we want the power series for G knowing the power series for F. How do we get the power series for F?
Integrate.
So let's. So first, let's build the power series for F. So the power series for F, we know the power series for 1 over 1 minus x is that with, right? So that's 1 over 1 minus x. That's the geometric. And then we switch to the alternating geometric by replacing x with negative x. And if we replace x with negative x, we get this. So nothing has changed with the interval of convergence. And then we replace x with x squared. So we're replacing x with x squared. And if we replace with x squared, we already looked at that a little bit. That's not going to change the interval of convergence. So now we're there. That's where we're at for F. What's the last step? We're almost to F. We're not quite there. We're almost there. What's the last step? Multiply by x. And does multiplication by x change anything in terms of the interval of convergence? No. So now we multiply by x. Now we have the power series for F. We constructed it. So when we multiply by x, we have to add 1 to the exponent in here, and that is not going to change the interval of convergence. Now we have the integral. Now we have the power series for F.
So it would not be x to the 3k at that point?
Not yet. So now to get to what Austin had pointed out a minute ago, how do we get to G from F? Integrate. So if we integrate x over 1 plus x squared dx, what does that integrate to? Well, it's in log form if we do this kind of thing. So this is going to be 1/2 natural log. Don't need absolute values because the denominator is never negative. So we get that. So we'll stop there and we'll finish this one off on Thursday in the first few minutes of class. And think about it ahead of time. Think if you can figure out what the power series for G will be. He's out of here. He's like a rocket.
Who, me?
You. He's like a rocket.
Who's the highest I've ever seen? 50%. That's what my physics